Hello and welcome to today's webinar, organised by the Pathologist and FFEI. I'm Olivia Gaskell, Associate Editor of the Pathologist, and I'm excited to be moderating today's webinar, where we'll discuss the latest thinking in the area of colour fidelity in digital pathology. Please allow me to introduce today's speakers, Andy Cook and Richard Salmon. Andy is CEO of FFEI Limited. He has a background in electronics engineering and over 30 years' experience, 20 of which have been with FFEI, leading teams and businesses in the field of digital imaging, colour management and colour fidelity. Richard is the Business Development Lead for Life Science Technologies and is responsible for elements of FFEI's diagnostic and life sciences technology development, partnership formation and strategic contributions to the company's growth in the life sciences market. During the webinar, our three speakers will highlight the importance of validating and standardising the colour of digital images produced by whole slide imaging devices and share the latest thinking on how to ensure colour fidelity within your digital pathology workflow. They'll be on hand to answer any questions that you may have at the end of the presentation, but please remember that you can submit questions at any time throughout the webinar. So without further ado, let's get on with today's webinar. Andy, over to you.
Thanks, Olivia, and welcome to this seminar. Thanks very much for joining. As Olivia mentioned, I'm the CEO of FFEI Limited. We're based in Hemel Hempstead, just north of London in the UK. Our company are specialist designers and manufacturers of digital imaging technology with a history of innovation dating back over 70 years. As an electronics engineer, I've always been fascinated by colour imaging technology. And when I qualified about 30 years ago, I had the opportunity to join Crossfield Electronics, a company who in the early 70s developed the world's first commercial colour scanner used in the reprographics market. In those days, it was used to scan and digitise photos, used in newspapers, magazines, books, and other printed material. Actually, it was quite an exciting industry with lots of investment going on in all sorts of new technology and software, all related to digital colour and image manipulation. When I joined in the 80s, the company had become one of the most successful colour scanner manufacturers in the world. And it was a very exciting time with lots of new product developments and launches going on. Crossfield evolved in the years ahead with the advent of digital cameras and desktop publishing, and it was acquired by Fujifilm. That was an interesting era as Fuji invested very heavily in our digital imaging technologies. More recently, in 2006, I was privileged to lead a management buyout, and we renamed the company to FFEI. And we were given the freedom to invest much more broadly in the world of digital pathology. During my career, I've been lucky enough to have worked with some of the leading digital colour experts and teams as we developed more and more advanced scanning technologies. Actually, most of my career has been spent with teams pushing the boundaries of digital colour and its application. It was almost 20 years ago that one of our clients started using one of our high-end photographic scanners to digitize human tissue. It was all very crude in those days, but it did open our eyes to the future possibilities for digital pathology. Our first real digital pathology scanning device was launched in 2004. And although quite basic relative to today's technology, it provided a very good base to develop a bright field whole slide scanner, which we launched in 2009 and actually became a major success for us, winning a Queen's Award for Innovation in 2003. As we learnt more about the needs of our pathology clients and the whole workflow challenges, it became apparent that for digital imaging to really become mainstream and a game changer in pathology, there were several technical challenges needed to be overcome. Firstly, the speed image quality ratio needed to dramatically improve to match the overall throughput requirements of a normal lab. Secondly, the subject of today's webinar is the colour fidelity and accuracy of each image needed to better reflect the truth of the original slide. Basically, in those days, most digital images, when viewed on a screen or monitor, did not actually truly represent the, let's call it, ground truth of the original when compared under a microscope. This, we found, represented not only a major challenge for pathologists as they viewed and tried to understand the issues within the tissue, because they have years of experience using microscopes, and now they're looking at a digital image which perhaps doesn't quite truly represent the original slide. But the other issue was one for the automated image recognition systems and software that were starting to be developed at that time. And they were struggling to identify some of the specific features within a digital image. So with these two subjects, we embarked on a couple of major government-funded research programs that went on for a couple of years. One of those research programs helped us develop very high quality scanning at high speed, and that technology now forms part of the imaging engine within the Ventana DP200 slide scanner. In fact, that technology recently won us another Queen's Award for Innovation, which we celebrated just a few weeks ago. The second research program the output was a product called Sierra, which is our color calibration technology, and we're going to be sharing more of that with you today. Specifically, the research enabled us to identify materials that could be used in a calibration slide like this, and the materials represent or have characteristics of human tissue when scanned under a digital device. So what we're going to do is I'm going to hand over to Dr. Richard Salmon, who's going to explain much more about this technology, why it's needed, how it's applied, and also he's going to touch on some really interesting research that's been going on around its effectiveness in a number of different applications. So anyway, without further ado, I'm going to hand over to Richard, who's going to take it from here, and I hope you enjoy the rest of the webinar, and we'll see you a little bit later. Thank you.
Hi, thanks for attending. My name is Rick, and I'd like to talk about the QA impact of validating and standardizing ground truth color for digital pathology. The scanning devices inside your lab could be thought of as black boxes in which a physical tissue slide is put in one side, magic happens, and a digital image is output for onwards analysis. You may also have seen in your own labs, sometimes the same piece of tissue can go into different black boxes and can lead to differently colored outputs, as shown here. And this may have implications on downstream diagnosis and QA processes. What causes this color variation? Well, the different manufacturers of scanners use different designs for the different modules within each scanner: sensors, lenses, illumination, image processing. And therefore each device has a different profile for how it captures an analog image and converts it to digital. What can be done about this color variation? Well, the FDA have identified this issue in recent guidelines and proposed a framework for system-level color reproducibility. In reality, this requires the use of an independent known reference target slide, which can follow two routes. Firstly, the spectral truth of the color captured within that slide can be measured. And secondly, the same slide can go through an imaging system to be assessed, which produces an image that contains the color artifacts of that black box. And therefore, this provides the data sets to calculate color accuracy, which can be reported for QA processes. At the same time, this data can be used to calculate an ICC profile, which can correct or calibrate all the images that leave these scanning devices back down to the original truth of the target slide. So what does meeting this FDA framework with an independent target slide achieve? Well, CIE delta E2000 is a measure of colour difference from absolute colour, with humans capable of resolving delta E of around 3 or 4. A delta E of 5 is therefore unlikely to have significant impact on diagnosis. As you can see in the bar chart, using an independent methodology enables the standardization of highly variable industry-wide colour, as well as correcting individual scanner accuracy. In addition, scanner colour is part of the end-to-end pipeline, from patient to tissue to diagnosis, on a monitor or by AI. It's therefore important that colour fidelity is maintained to map and align the digitization process of real tissue colour as it is presented to a digital pathologist, as shown plotted on the right. To enable this, FFEI have developed the Sierra Slide, which contains small patches of biopolymer that binds to pathology stains and therefore mimics the interaction of stains with tissue to a high degree. This also enables the creation of the whole gamut of pathology colours that each scanning system might encounter. And it is there also formatted like a pathology slide, so this complements FDA guidelines and promotes interoperability and simple adoption. To ensure that the methodology and outputs can be trusted and adopted, calculations and file formats that are used meet ISO standards, and the ICC profiles produced are DICOM compatible, and with FFEI expertise forming part of the ICC Medical Imaging Working Group. FFEI have got a few simple but important principles for colour calibration. The provision of quantitative data to establish metrics for reporting for the purpose of accurate validation. Calibration, providing a corrective method to ensure that all data produced is of the same quality. And standardization, scanner agnostic interoperability that enables universal human or AI analysis from real colour, irrelevant of scanner type, age, or location. And this provides a route to quality assurance and not quality approximation. Here you can see some qualitative data, and on the left-hand side, this may be data that you've seen in your own labs, where you put the same piece of tissue into 2 different scanning systems and get 2 differently coloured outputs. However, you can apply these Sierra ICC profiles on the right-hand side, and now not only do images from either scanner become highly standardized to each other, but they also most closely represent the reality of the colour in the analog tissue slide. When assessing scanner colour outputs, it can be seen by the human eye that there are huge raw colour errors introduced by whole slide imaging. And this is shown here by analysis of 3 scanners from 3 vendors that compare the colour output by a scanner to that of real ground truth colour. However, by using the Sierra methodology, these errors can now be quantified across the whole gamut of pathology. Quantification also reveals that scanner-to-scanner spread of delta E is not uniform. Differing distribution of errors across scanner systems further decreases standardization. And visually, humans can see the improvement by applying the Sierra slide, but now importantly, can validate and standardize to decimal place accuracy, which is often well below the ability of humans to see, but not perhaps AI. And this forms the basis of a practical validation process. Industry-wide metrics are available for assessing the current state of play, as seen in the top left, or for measuring onwards consistency for QA or GLP. And there is also the ability to calibrate and maintain accuracy to achieve realistic QA levels, as shown in the bottom right. And therefore, the situation now is not a pass-fail, but a pass, fail and fix to ensure that onwards use of all precious tissue data is possible. I'd now like to demonstrate how FFEI can enable you to discover the colour validity and standardization of your own data through use of the Sierra VS analyzer. The VSA package comes with FFEI's patented Sierra calibration slide, a downloadable Sierra VSA software for Windows 10, with an activation code for slide identification. It also comes with a user guide, and analysis reports can be exported from the software in due time. Integrated viewing of the pathologist's own tissue samples with and without ICC profiles applied has been included, alongside FAQs and support through the FFEI support database. So to begin, we launch the application, which is run on a Windows 10 platform. We put in our password to log in, and this opens up the main Sierra VSA window. The next step would be to enter your slide serial number, and when prompted, the activation code supplied on first use of the slide. And as you can see here, you will have a snapshot view of the number of profiles or analysis credits you have left, and also the expiry date, the validity period of the slide itself. Next step is to upload the image of the slide scanned on the scanner to be investigated. So now what's occurring here is once a OpenSlide compatible image has been uploaded, the RGB color is extracted from this image of the slide and sent to FFEI server. So no image data leaves the install site, and only kilobytes rather than gigabytes of data are transferred to encourage high speeds and more usability. Then the color analysis is returned from FFEI, and there's also provision of a history tab to enable the recall of up to 5 different analyses for future reference. Once the color data has been extracted from the uploaded image, you simply press Analyze, name the description for this particular analysis, and create the analysis and the profile. And this occurs on the FFEI server within usually a period of around 30 seconds. The more time limiting factor of using this is the time required to actually generate the slide image on the scanner itself. So as this profile returns and the analysis returns, each patch here will show the color output from the image in the bottom left, and in the top right will show the real color expected from the image. The top panel shows the raw image before ICC profiling, and the bottom panel shows after ICC profiling, with the quantitative delta E values for all these patches on the Sierra slide also reported. And as we discussed before, delta E is a standard measurement that quantifies the color difference from absolute color truth, with the delta E level as close to 0 as possible being better. For human diagnostic purposes, we propose a threshold max delta E of 5 is widely considered more accurate than the average human vision capabilities when looking at tissue samples. And so here you can see we have also reported, for the purposes of quantitative validation, the mean and maximum delta E in both circumstances. And this is displayed on the top of each of the panels here. In this example, you can see that without Sierra, the maximum and average delta E's are far above the threshold of the delta E of 5, whereas application of Sierra, both the max and the average delta E are well below this validity threshold of 5. For qualitative analysis, FFEI have integrated a viewer into the VS Analyzer. To use this, simply select the icon at the bottom left and upload a tissue sample that has been scanned on the same scanner that the Sierra slide was also scanned on. The software will then automatically apply this ICC profile to the chosen tissue, and the viewer provides several functionalities. Firstly, there is a side-by-side synchronized view so that you can zoom into cellular level detail and compare a fixed point of tissue from without the Sierra ICC profile to with the Sierra ICC profile. And there is also a swipe functionality to enable the analysis of one single position in the tissue with and without the profile applied. For example, I'm looking at these group of nuclei here, and I can look at the effect with and without the profile. Multiple instances of this viewer can be opened to enable analysis of different tissues from the same scanner, or to use the History tab to enable analysis of the same piece of tissue across different scanners. And so therefore, there is also, alongside a resize function, a rotate function to allow for ergonomic alignment of different pieces of tissue from different scanners. For ongoing reporting and QA, a report function has been included in the software, which will produce all of the information that has been gathered by the quantitative analysis and put it into the format of a savable PDF, as shown here. This contains information about the identity and time and location of the analysis, reiterates the quantitative output of before and after application of the technology across all the gamut of pathology, contains information on ICC and CIE to help for interpretation of data, and also presents some basic analysis of the process to influence QA processes and establish the distribution of errors within your own systems. There's also an FAQ provided to connect to FFEI if there are any further questions about this analysis, or if you wish this report to be tailored to specific applications. I would now like to present a selection of case studies that utilize and are enhanced by Sierra in different ways. In this first study, an alternative to color calibration is considered, following the reasonable logic of standardizing using only the same model of scanner, or device control, and measuring the colors used across all of pathology, as shown in the middle here. Here are data from 11 of the same scanner model, and we see that the average raw color variation between scanners is nearly 3, with variation in some colors higher than in others. However, this variation in scanner color, and therefore the variation potentially inherited by tissue images, can be reduced by over 8-fold on average by Sierra. So what is the impact of this on tissue analysis? It indicates that device control is not enough for color fidelity. Furthermore, looking at the raw color differences from the same 11 scanners shows an average error of nearly 15, some 4 to 5 times that of average human visual resolution. Of particular note was the high color variation and error in pink and purple. And these parts of the gamut are of course important for the incredibly common H&E tissue stains. As color variations are an inherent side effect of whole slide imaging digitization, it's fair to say that this will occur to some extent in any scanner on the market, and so is an industry-wide occurrence. However, application of the Sierra technology brings average errors down to baseline, as you can see here, and well below the ability for human beings to differentiate between scanner output. This therefore indicates that color calibration will have an impact on QA, even when data comes from the same scanner models, and that the distribution of errors can be quantified as part of universal metric-based reporting. In addition, it poses the question, if this occurs in a single scanner type, what happens when data from multiple sites and multiple scanners are used together? To demonstrate this, a second case study is looking at the impact of color standardization on multi-site AI. Our collaborators at the Karolinska Institute have developed a prostate AI that performs better than humans in a controlled environment. We are investigating the ability of Sierra to standardize images to the ground truth from many scanners in many locations, to test the ability of the AI to retain its high accuracy when deployed in relatively unreliable scanner environments, such as might be found in clinical practice. This also provides an added layer of QA for the adoption and onwards validation of AI diagnoses. In a third study, FFEI are part of the National Pathology Imaging Cooperative in the UK, led by collaborators at the University of Leeds and the Leeds NHS Trust. This represents a nationwide programme of digital pathology for which FFEI are deploying Sierra in a first-of-its-kind cross-site medical QA programme. The impact of validating and standardising colour data across this many petabyte repository will enable the development of an adoptable, independent QA methodology for real clinical data, and also enable the regulation and accreditation of AI that evolve from the consortium. Finally, FFEI have created a view of the modern landscape of colour, collating data from different scanner images of Sierra that are applied in different ways, such as for multi-site clinical digital pathology, cross-lab pharmaceutical research, scanner manufacturing, and AI software development. Many of these uses are also highly collaborative and rely on image sharing. However, if you were to pick a direction of travel before calibration, shown here in the bottom left, you can go across all the colours or follow just one colour as such. And the terrain is uneven and difficult to navigate, making individual data sets hard to reliably connect. However, once Sierra is applied, you can now see that the way is smooth, reliable, and predictable across all colours and data sources, and importantly, falls below the quantitative values detectable by human qualification. This not only demonstrates it is possible to achieve universal validation and standardization for digital pathology, but it also enables humans and AI to collaborate on comparable quality data that is accessible, interoperable, and reusable. I'd like to thank the team at FFEI for all their excellent work, and also our collaborators at the Karolinska Institute, the ICC, and NPIC in Leeds, as well as UKRI for funding. If you think Sierra and FFEI can help enhance the impact of your studies, please do get in touch.
Thank you to Andy, Mark and Richard for your insight into the latest thinking in the area of colour fidelity in digital pathology. We've received a number of questions from audience members, so we'll try and get through as many as we can in the time remaining. But please be sure that any questions that aren't answered live today will be answered via email. Also, you'll be seeing the poll results that you've answered throughout the presentation pop up on your screen shortly. Okay, so our first question is, how many scanners can I calibrate with one slide?
Hi, this is Rick, and I'll take this one. So the Sierra Slide itself can work for 100 scans. So the user could choose, for example, to use the slide across 100 different scanners, and it's a scanner-agnostic format. It can be functional with any scanner on the market. But also users may choose to compare individual groups of scanners, 3, 4, let's say, over time to establish any change or drift, as we refer to it, in the colour of those machines over time, or in fact have a 1 or 2 regular machines that they want to implement a routine procedure on, so to on a frequent period of time use the slide to keep that calibrated. So the top level answer is 100 machines, but the functionality of the slide on all those machines is entirely user dependent. Thank you.
Okay, great. And then does the Sierra Slide have a shelf life?
Mark, do you want to take that?
Yeah, hi everybody. Yes, it has a shelf life of 12 months, in which case you can obviously order another one to obviously help you calibrate again further on for your continuation of QA on your scanners for the following years.
Okay, and then what are the implications for not colour calibrating my portfolio of scanners?
Okay, great question. I'll take that. Obviously, calibration is all about bringing standardization. So if you're not calibrating a device in your workflow, you're not sure necessarily where it is in terms of how it's interpreting color. So at a practical level, that means that if you've got the same sample and you're scanning it on 2 different devices, that are not calibrated, then you're going to get different results. What this technology does is unifies the capability and how the color fidelity of the image is captured and then replayed. So if you calibrate, you have much more confidence that the same sample on different devices is going to look the same on screen. Thank you.
Okay, and then the next one says, it is intuitive that colour correction might be important for training and accuracy of AI to augment pathology interpretation, but how important is it for pathologists rendering diagnoses using digital pathology systems?
Another great question. I'm going to throw that to Rick. Do you want to have a go at answering that?
Sure, of course. Thank you. The effect is quite obvious on the different colours between with and without applying this profile on actual tissue samples. One example may be if the definition of colour isn't accurate between areas of similarly coloured interest. So, for example, in the nuclei of a cell, it may be difficult for a pathologist to visually resolve some of the internuclear detail, for example, if all the purples of the hematoxylin blend in together poorly. So this technology allows very precise pixel to by pixel definition of colours for that purpose. And then also, I guess the driving force of it, as you mentioned, it's very influential, likely to be influential on the standardisation of AI. However, in the reality of a growing pathology field, it's quite clear that to be able to make sure you've got your standardised data for your QA purposes, that you know that at every step of your end-to-end pipeline of pathology, you've got quantitative accuracy, lends weight and confidence to the pathologist as they go forward into diagnostics. Thank you.
Okay, and then once the Sierra slide has been scanned and analysed, how does the colour profile get applied to the scanner to correct the image for future scans? Does this require cooperation from the scanner manufacturer?
Rick, another one for you.
Yeah, thanks. So there are various points in the, should we say, the end-to-end pipeline of the digitization process and the viewing process that the profile can be applied. In one format, you're quite correct. Interaction with the scanner manufacturers can allow for these profiles to be embedded at the point of writing an image, and so that intuitively these profiles and all the high degree of accuracy and standardization the slide provides can be there in the raw image. But in perhaps the more modern scenario, where there are multiple people using multiple scanners, different models, different manufacturers, you can also apply these profiles at the point of viewing. For example, in a viewer you're developing yourself or an AI system you're developing yourself, these profiles can be used to convert all of the color data into a standardized universal color space, for example. And therefore, there's also the opportunity for FFEI and end user and commercial viewer vendors to work together to implement this in, let's say, a Sierra toggle switch, for example. And this enables raw data to still be kept as raw data, and at the point of viewing, switching on the Sierra ICC profile to standardize those images for either your AI purposes or your human diagnostics. Thank you.
Okay, and then the next audience member has two questions, so I'll split them up. So the first they've asked is, what is the thickness of your calibration slide? My Hamamatsu scanner only accepts slides of less than 1.3 millimeters. That was the first question.
Rick, do you have the answer to that?
I do, thank you. So the thickness of the Sierra slide is just over 1.375 at 1.375 mil, but our experience with a whole range of scanners, including Hamamatsu scanners, amongst all the other manufacturers, have never encountered the thickness of the slide being a direct issue. So what I would say is we can have a talk offline. And we can see if we can help you out, basically. It might be an opportunity for us to have a look with you. Thanks.
Okay, and then the next question that the same audience member has asked is, if I have an IA project with 500 digitized slides, do I have to correct colour for all the 500 slides?
I'll jump in and take that one as well. No is the answer. So if you've got 500 digitized slides from the same scanner, depending on an established, say, color drift of that scanner, it should be entirely feasible to use the one correction for all of the slides. However, if you have 500 from 5 scanners, for example, you would make 5 corrections, one for each unique scanner. Or perhaps if you were to have your 500 samples, but they've come over a long period of time from a few scanners, it would be most ideal if you could apply a correction that's most closely to the point of data collection. So it would largely depend on your actual collection method for those slides, but it does not require one profile per one image. Thank you.
Okay, so then the next question is, what is the colour space and white point used for calibration?
Rick, do you want to pick that one up as well?
Yeah, sure. We put the current colour space into X, Y, Z colour space, and this is for the purpose of preventing some clipping of some colours that can occur in smaller spaces such as LAB. And in terms of the white point used for calibration, we use, we've got the white point is essentially emptiness. You know, it's an empty part of the slide that calibrates the absolute white coming through the slide itself. And we often suggest setting the value of around 95, 93, but it depends on a scanner-to-scanner basis. And of course, we can investigate this should you wish to test that. Thank you.
Okay, and then has the colour standard been used to assess image viewers built-in software? Sorry, let me start again. Has the colour standard been used to assess image viewers built-in software automatic colour correction? So they've provided an example here of the Leica Apero colour correction. How do we know if this automatic correction is sufficient?
That's a very interesting question, actually. So the answer to that is we do have various data on and off in terms of scanner manufacturers' own colour correction technology, and it's quite interesting to see the variations. Some are much better than others. It's not data that we typically publish, but there is generally the scanners are able to provide raw data which we can use to check the calibration, but they also in many cases have their own colour calibration technology. And so the answer is yes, we generally can assess the colour calibration of scanner manufacturers' own viewing technologies. Thank you.
Okay, and then can I calibrate my IHC DAB stained images as well, or does the calibration slide only work for HEs?
Rick, do you want to explain the breadth of what's possible for calibration?
Of course, yeah. Thanks, Suzanne. So no, the slide itself is made out of lots and lots of different, as we mentioned in the presentation, lots and lots of different patches that are stained for a whole range of the different colours that you might, that a scanner system might encounter. And so in there is parts, there's every single part of the gamut, not of colour itself, but also the gamut of colours expected in pathology. So as you will probably have seen, obviously there's a large focus around the H&E aspects of things, because that makes up not just a large majority of the samples out there, but also because it's an area that needs to be quite carefully defined as a very broad stain. So in terms of the precision of your IHC and your DAB stains, there's still parts of the slide there that would account for the calibration of those parts of the gamut as well as special stains such as into greens and oranges and yellows and neutral, and as well as the brown itself. So you're not limited to H&E. You would be covered by your IHC and DAB, but it also doesn't stop there. There's a whole range of things that you would be able to use. So thank you very much for that question.
Okay, and then what will be the role for colour calibration with increased use of pseudo-colouring to visualise multimodal staining techniques and methods such as spatial transcriptomics?
Well, that's a big question. Hey, Rick, would you like to have a go?
Yeah, I think there's a cup of coffee in that one, Keith, to be honest. But whilst I understand the concept of pseudo-colouring to the point of identifying specific part of the cells and the images themselves, and therefore maybe the raw data or the pure digital data is not of incredible concern in the pseudo-colouring element of things. It's all supportive. It's all part of an end-to-end process. So I'm sure the phrase "sum greater than its parts" springs to mind for myself. So yes, whilst you can have multimodal staining techniques and spatial transcriptomics and all the different genomic techniques, it's more an element of how does everything come together to make that perfect diagnosis or the perfect research platform to extract the most amount of information. And I believe bright field technology will continue to play a role in that, and therefore the role for colour calibration and making sure your data is standardised before you start applying these multimodal techniques will maintain its need for fidelity, and also will play a part in that combinatory effort of everything moving forwards into releasing more information from each sample. Thanks, Keith.
Okay, well, great, thank you. I'm afraid we're going to have to leave it there. Again, let me reassure audience members that any questions left unanswered today will be answered after the event by email. The webinar will also be available on demand in just a few days' time, and you'll receive an email alert when it's ready. Thank you once again to our speakers for presenting, and thank you for everyone for joining us today. I look forward to seeing you at future webinars. Goodbye.
Thank you.